Good afternoon, everyone. So I'm Purba. Today I'll be talking about data-driven reconstruction in cosmology with mainly emphasis on the late-time physics. So as we all know, like recently, the late-time accelerated expansion of the universe has been our greatest puzzles. And to accommodate for this accelerated expansion, the cosmologists have introduced an exotic component in the energy component of the universe, and we call it the dark energy. And the simplest model for dark energy is our cosmological constant lambda. Now, lambda together with CDM forms our standard cosmological model. But there are several theoretical problems associated to lambda, like we have the cosmological constant problem and the coincidence problem. So several alternative models have been proposed. Now, still, lambda CDM remains the simplest model for us to understand all the cosmological observations. And the parameters governing this lambda CDM model have been tested or have been measured with a very good precision. And we find that from different observations, from different sets of observations, we arrive at different kinds of inferences. So these have led to something known as a tension in cosmology. The most two well-known are the Hubble tension, which is basically presently the 5 sigma tension between the value of H naught measured from the model-dependent Planck estimates versus the model-independent Schurz calibration, and the clustering tension in the from the Planck versus the other galaxy clusters. So what we try to do is, like, instead of trying out some cosmological models, we try to directly reconstruct from observations the evolutionary history, and this works as a reverse way of building a model from observations. So there are generally two trends that are followed. One is the parametric reconstruction, where we assume a parametric model of this form, where theta are my model parameters that are estimated from observational data. Another is a non-parametric reconstruction, where we actually try to build up the functional form directly from redshift without assuming any particular model parameters. So the main cosmological parameters which are involved in this game of reconstruction can be broadly divided into two categories. That is the kinematical or the cosmographical quantities, which are defined as time derivatives of the scale factor, and the dynamical or the physical quantities in the Friedmann equations. So there are therefore non-parametric methods for reconstruction. So today I'll be mostly focusing on Gaussian processes. So this is an overview of how the reconstruction works. So suppose we have a data set, and this data has been sampled from a Gaussian distribution. Now our aim is to reconstruct a function which describes this data set. Now, if f is a function that is reconstructed from this algorithm, so it has an underlying mean function and a covariance function. Now this covariance correlates the values of the function at some redshift and its neighborhood point. Now there are different covariance functions available in literature. So I have written down a few of them. Now this covariance function depends on some hyperparameters, which basically determine how our reconstructed model will likely behave with redshift. And we optimize or basically do MCMC to marginalize over these hyperparameters by maximizing this log likelihood. Now with this optimized covariance function, we can make predictions on a given test set of redshifts. So today I'll be mostly talking on three problems, like whether our underlying cosmology is lambda CDM or do we need modifications to that, about whether interactions exist within the cosmic dark sector, and the curvature of the universe from determining or constraining the curvature density parameters of the universe from model independent observation in a model independent way. So first I will talk about the reconstruction of the jerk parameter. Now we all know that the universe is undergoing an accelerated expansion. So the next higher order derivative we are interested in is the third order derivative of the scale factor, that is the jerk. So for lambda CDM we know J is 1. So any deviation from J equals to 1 will lead to a model which is different from lambda CDM. Now we assume that the universe is spatially flat and homogeneous on large scales, and there is no dependence made on the theory of gravity and no assumptions regarding the distribution of matter. So the jerk parameter can be rewritten as a function of my observables, the Hubble parameter, and the co-moving distances as a function of redshift. Now, these are the data sets I have utilized to reconstruct these functions. And so here are the plots for the individual data sets. So we find that J remains very close to 1 in the low redshift and has an evolution for higher Z, and for some parts of the evolution, J even leaves J equals, so our reconstructed curve leaves J equals to 1 in 1 sigma, but that is always included in the 2 sigma of the reconstruction. So it is possible that J might have a non-monotonic evolution. So to check the effect of different H0 values of H0 from the 2 Planck and Rees priors, we have done the reconstruction of J for the Hubble and the supernovae data, and we have compared all the results of all the 3. So we find that there is not much of a significant difference in the results if we are trying to reconstruct the universe. Next, I have shown the possibility of the existence of a non-gravitational interaction in the cosmic dark sector. So the underlying assumption is that dark matter and dark energy do not evolve independently, but there is a transfer of energy between them, and we have tried to reconstruct this quantity Q. Now, we do not know what this quantity is, like what this kind of exotic interaction is, but if something of an interaction exists, it will make its effect felt via this transfer of energy. And we see that for low Z, Q remains mostly close to 0, indicating no appreciable interaction in the present epoch. Negative values of Q, we can see the negative values of Q exist, but it is still included within the 2 sigma confidence level. So the possibility of an interaction may not be ruled out for higher Z. And here I have plotted the evolution of the density parameters, the omega m and omega d, for the interacting scenario. These colored lines are for the Lambda Celium model. So next, I have revisited the non-parametric reconstruction of the deceleration parameter using the growth rate of structured data. Now, for the growth rate of structured data, we know that what we measure right now is the quantity called F sigma 8. Now, Euclid will soon be giving us measurements directly about F and sigma 8 differently, but right now we are limited to this quantity. So we assume an approximate solution of this form for the growth rate, and we find out the constraints on omega m and gamma by minimizing this chi-square by using a Markov chain Monte Carlo here to arrive at basically E. Now, once we get E, we can plot the evolution of the deceleration parameter for different values of the omega matter. So this is the result we have obtained from MCMC, and these two are the values, the one from the Planck priors and another from the supernova compilation. So we see that using the growth rate of structured data, we arrive at different evolutionary scenarios. So the value of omega m plays a significant role in the evolutionary history of our universe when we are working with the growth rate data. Now, we want to find out, or rather we want to obtain constraints on the curvature density parameter, because recently the Planck estimates had shown us a possibility for the existence of a non-zero spatial curvature. Now, we know that for during inflation, if omega was very close to 1, if omega is very close to 1, that is omega k is very close to 0, it was not a problem. But when the universe expanded and it went through a radiation and matter dominated phases, if omega k was not exactly equal to 1, k will make its effect felt as the universe evolves. So here I have used the background data sets and the RSD data sets to obtain the constraints on omega k and some cosmological parameters without assuming any cosmological model. And these are the plots. So this is for the background data sets, and this is using the RSD data set. So we see that omega k is very close to 0, and the omega k equals to 0 is always included in the 1 sigma. For the RSD data, we see that the value of omega m is lesser than the value obtained from Planck, and omega k equals to 0 is included within the 2 sigma confidence level for the Planck and for the Rees prior. But in case of the Planck prior, we need to move till 3 sigma. And these are the values of the growth rate of structure. So for Lambda Celium, we have it like 0.55. And so we find that the Lambda Celium model is included in 2 sigma here also. Now we try to make some forecasts on some gravitational wave missions like the ELISA and ET using this GPR. So we take 6 representative models and generate the DL versus Z catalogs. Now using these fiducials from these representative models, we reconstruct HZ and we code the value of H0 for each of the cases. Now what we find is, like for this is the results for the existing constraints, and this is what we get from ELISA and ET. So we see a significant shift in the mean positions, means in the value of H0, and relaxed error bars for each of these models. So we have to test it for other machine learning algorithms too, and this is some trends we observe. Now, I would like to discuss some of the main caveats about GP regarding the kernel dependence. So there are a lot of kernels available in literature, so we have to precisely choose, like undergo some kernel selection algorithms before working on our problems. There is a mean function, so in generally the mean is chosen to be 0 to make it cosmology independent. So we have to look for like the dependence of mean functions. There are studies regarding that. Now we are considering redshift binning, like reconstruction in different redshift intervals to look for different signatures, like if it affects our present constraints or not. And we have studied the effect of different cosmological priors on our reconstruction. Now we should also look for alternative machine learning algorithms like machine learning algorithms and neural networks and or genetic algorithms and likelihood free inferences, and likely we can try to make forecast on future missions when the data arrives. So
thank you.
I would like to thank the organizers for giving me this opportunity and all my collaborators.
Do we have any questions?
So when you say, when you were mentioning BEO data,
yeah,
you were putting H of Z as the observable?
H of Z as the
or E of Z in reality. But then my question is whether you're using BEO data along and across the line of sight. So you are using the integrated E of Z and the E of Z with the proper covariance, or you're using only E of Z?
Oh, with the covariance. So I'm using like DH scaled over RD and the DM scaled over RD together with their covariances.
Okay, have you studied the equation of state parameter?
Yeah, I haven't put it here, but I have.
So if it is not Lambda Celium, so how it favors, so it is quintessence or something else? What your data says basically, if it is data driven?
Like we observed that for when we take a Planck prior, we find that it favors a phantom non-phantom equation of state, and when we are working with the Rees prior, the best fit curve, it shows a dip from the W equals to -1 line, but that is always included within 1 sigma. Like, but when we, if I show you these plots, so this is a signature we observe for the equation of state 2 for when we are working with the RSD data. So this is just reflected there too.
Basically, Lambda Celium model is not ruled out within 1 sigma.
No, not for the early, like for the very late times.
Okay, one question more. So if you are taking the values of H0, for example, for different or omega, or you are also talking about the, so you are taking the flat universe prior, then how it is the model independent? So you are taking some model and so you are imposing that it is flat.
Here, so when we are using the distance data, we have to assume a spatial flatness, but nothing else is being assumed. For the Hubble data, like it is directly the data and there are no assumptions being made for the jerk. For the interaction, we have to assume a particular model because else we cannot write it in terms of these Friedman equations, but we do not assume any particular form of this Q. And for the RSD data, we have to make this linearized approximation for the growth rate.
Yeah, last question.
Hello. So there are, I see there are larger error bars and large redshifts. So are this because there is low data there?
So there is less data. That is one problem. And one could always try some mean functions to get a reconstruction about that mean. But that is like you are introducing some additional modeling to the data, so which I have ignored here. But I have seen results where I have tried them mine also. So if you use a mean function to do that, your reconstruction will lie about that mean. So your error bar will be reduced, but that means additional model dependence.
So but can we do something like this? Like we predict at one redshift and use that again back as my data. So can something like this be done?
Data generation that could be applied, like there are different data generation algorithms. So you can just insert, you have two direct data points and you can just simulate additional data there, keeping that information about its boundary fixed. Like I think there are algorithms that can do that.
Thank you. We can discuss that.
Let's thank the speaker again.